So Curtis, take it away.
Hey Dan, thanks for the introduction. So um, today, Applied Controls and Geometric Solutions is bringing you this webinar, and there we go. So Applied Controls, they are a local employee-owned company that is a distributor of automation equipment and software and robotics, and they're here to help educate. That's one of the reasons we have this webinar series. But working with Geometric Solutions, we have 60 plus years in the manufacturing business, and we use the digital twin to optimize these manufacturing processes. So we're going to talk about that. We support many industries. We're based out of the Midwest, so we do a lot of automotive, aerospace, medical, consumer products. We're not just, we support many industries because we have many different types of customers that need that type of work. And, we use the digital twin to do many things: improve quality, simulate and validate, before you start. We want to make sure that we catch the errors. And I like to call it a crystal ball, see into the future and fix any problems before I get to the plant floor, and it gets very costly to fix them. So, but the partnership between Applied Controls and Geometric Solutions, Applied Controls sells you the hardware and the things that make your plant work, and we can digitally simulate that and test it all out in advance to make sure that you have a successful launch when you get to launching your products. So with that, I call this a crystal ball. The digital twin is a crystal ball. Let you see into the future. We're going to talk about that and some of the ways that we use that. But first, let's watch this video. Oh wait, I'm sorry, that's the next slide. So digitalization changes everything, right? There's a lot of data out there, but I mean, things have changed, over the years, and done things traditionally have very changed. I mean, if we look at stuff like, we used to go to bookstores, now we get ebooks. We used to go to a record store. When was the last time you seen a record store? It's all online streaming. Yellow pages, now it's all on your phone and through Google searches. Ride sharing versus taxis. Things have changed drastically in many different businesses, and it's revolutionizing, how things get done. The same thing with manufacturing. So the digital twin, what is it?
What would you do if you knew you could not fail? Skydive? Climb a mountain? Explore the world? Change the world? Make a new you? And what would you make if you knew you could not fail? This or this? How about this? What if we tell you you can fail-proof make anything you want right now? You can make anything with the digital twin. The digital twin links together design and production so you see everything, plan the details, prevent problems, and optimize the complete system. The digital twin makes it possible to adapt to new ways of working, gain flexibility, and deliver the toughest jobs at your factory in Germany and in Mexico. Just like that. Start today with the latest technology so you can realize that amazing product the world needs right now, and take the leap, conquer that mountain, explore the world, knowing you helped change the world. Let's make it together with the digital twin.
So that video started off with, what could you do if you knew you couldn't fail? And that's, the thrust of the digital twin. We're proving out that we're not going to fail, and we're going to succeed. So let's talk a little bit more about this. What is the digital twin? It refers to a digital replica of, potential and actual physical assets, processes, people, places, systems, and devices that could be used for various purposes. You know, it's really a twin of reality, and today's software tools can do that. So let's just talk about the digital twin in manufacturing. So I'm based out of the Detroit area, so I pick on cars because I know them quite well, but we have product design for a car, right? So that product is designed by, you know, GM, Ford, Chrysler, Honda, whoever it happens to be, and it's made from parts and then assembled. So if we look at the parts, there is a single stamping, but I have to make the stamping dies and the tools to make that stamping. For the assembly of the product, I have to make tools that assemble everything. So, you know, that single part has to be made, and there's manufacturing processes for that. And then the assemblies have to put it all together, you know, the assembly tooling. And we're going to talk about these manufacturing digital twins. There is another one for product. You know, you start looking at like finite element analysis for structural analysis, CFD, computational fluid dynamics. But this is focusing on manufacturing and making things and assembling things. So if we look at a systems diagram, the OEM team defines a product, that's stamping, right? And Siemens has CAD packages to model those up. But then we have manufacturing tooling. We have to design the tools, the stamping dies. And in addition, there's tools out there for die wizards, mold wizards, whatever the case may be. Then we have to manufacture the dies, right? So then there's CAM programs, things to manufacture the CAM, you know, the machines that make it. And then we have to validate things, and there's coordinate measure machines. And there's all types of these mini digital twins that put it together. But this is focusing on the parts. What I want to spend some time on today really is focusing on the assembly. So the parts we have, Siemens has this product, they call it a data integrated data model, where it's all coming out of one CAD package and they all talk to each other. So if I update my product design, my CAM updates, my CMM updates, but what we really want to talk about is the assembly tool manufacturing. So with the plant, you have plant layouts, and we have tools to help design the plants. A couple different ones, one based on AutoCAD and one based in NX. Assembly logistics, just making sure material flows through the plant. And there's a product out there called Plant Simulation for that. We have assembly station, robotic cells, where we're actually doing robotic programming, and the machines. So there's this Process Simulate and Mechatronics Concept Designer, and we're going to talk about each one of these. And then quality, we want to do the digital twin of quality, and there's tools out there to do that, 3D tolerance analysis, and plant data monitoring, so DPV, production dimensional product validation, DPV. So this is a digital twin of production, and we're going to focus on that for the rest of the webinar here. So the digital twin, the reason we use it is for risk mitigation. And if we think about this, industry is driving companies to have compressed timelines, increased quality, lower cost, innovation, right? But the individual manufacturing engineers that are trying to launch these plants want to make sure their processes are validated. They're going to meet their production throughput numbers. If they're supposed to have 100 units an hour, they can make that. Or if they're making 3 a day, that they're going to make 3 versus 2. We want to make sure that doesn't, they can make that, and the risks that go with that it's all mitigated. So the question is how do you mitigate your risk? Well, if I told you I had a crystal ball to let you mitigate manufacturing risk with your future product launch, would you be interested? And that's what the digital twin is. So, what risk can the digital twin mitigate? Well, throughput requirements, can we meet production targets? Optimized resources, do we have enough labor? Do we have too much labor? AGVs, do we have enough AGVs to support it, including battery charging stations? Bottlenecks, where are they? Can we identify them? Can we meet our startup production date, when we have everything debugged and working in time? Quality, what's going to be the quality of your build? Are you going to meet your quality targets for fit and finish, or just even functions? Will the part function? Mechatronic integration, the mechanics of the system works, and electronics. And big thing is we want to avoid recalls and improve customer satisfaction. So these kinds of risks the digital twin can mitigate, and we'll talk about these. So there's different tools that Siemens has, and the first one I want to talk about is plant simulation. And it's really great at the first three items there. Throughput requirements, trying to make sure you got throughput. Optimize labor, you can see I actually have humans in there, and we're actually making sure we have enough throughput, and I can actually do testing where I can add labor or remove labor and see how that affects my quality. If I remove labor, do I make, $20,000 worth of parts less than if I had that person? It might be worthwhile, because if it's $50,000 for the person for the year, but I only make $20,000 less, I'm still making more money. So bottlenecks, you can easily identify bottlenecks. There's tools in there, and we'll talk about some of those. The next tool is a product called Process Simulate, and it's really good at throughput, start of production. I'm actually, with this tool, it's focusing on robot and robotic cells, but we can actually make sure the robots don't hit anything. It can access everything. It has reachability. We can actually do the timing down to the millisecond of how much time it's going to take to do whatever the task is that robot is asked to do. And what's great is when we're done, we hit a button and it outputs the robot program. These robots in the simulation are virtual duplicates of the real robots, and kinematic links and their joints and what's happening with those robots, to the point of when I get done, if it works here, I hit a button and it exports that program, and my robot is ready to run. I don't have to do any robot programming on the plant floor, which saves time, and this is extremely accurate this way. The next tool we have is a product called Mechatronics Concept Designer. So the plant simulation tool talked about earlier is great at the plant level. The last tool, Process Simulate, is great for robotic cells, where there's a lot of robotic applications. And this is good at the machine level. So you can see here, this is a machine that's doing some packaging, and it's doing some sealed packaging, and there's a bunch of mechanical mechanisms moving along. And this tool is unique because it has a physics engine in it. And it's kind of based off of gaming technology, but you can see it's folding up the lids to this, and gravity's taking effect, it's falling down. So this is very physics-based, so it's very accurate. In fact, in a moment, you're going to see this box turn 90 degrees, and when it does it, it's going to tip. So, gravity's effect. That little red line there that it's going to hit is a sensor, it's a light sensor. And when it hits that light sensor, then that tray moves back. So it's great at the machine level, and it makes sure the mechatronics and the software code that runs it all works together. And the last area I want to talk about today is just, and there's products called variation analysis here, and what you're seeing is the variation between builds showing up. I can get statistical data. I have design of experiments tools in there that I can debug and fix it. But I can identify problems before I make them on the plant floor and fix them in advance, so I don't have that problem when I get into production, or worse, it gets out to the consumer and then there's recalls. So let's look at some case studies. I'm going to break these 4 tools down, talk them out a little bit, and some applications of where they've been successfully used. So the first tool I have here is called Plant Simulation. Plant Simulation is doing that. It's working with a plant. I can model machines, I can model processes, I can model people, I can model trucks, I can model warehousing. It's basically, I can emulate anything inside a plant. So here we had a customer that, I don't know if you remember a few years ago, 3D stereo was a new thing for television. Everybody had to have 3D stereo. You get the glasses, you can watch it in 3D. So this company had a line that you could see the barroom napkin sketch that we started with here, but it was an assembly line, and right on top here where it says, new 3D stereo, they added this little subline to the line, and when they added it in, they were having problems because they couldn't get the volume out that they used to. So we simulated it in plant simulation. We found out that that line, it was not any station that was in this line was slower than any of these. So, it was obvious that this was going to slow the line down. We put a buffer in here. These guys were working basically 9 hours a day, and everybody else was working 8 hours, and everything worked. But when we did that, we found we had a problem. And you can see these carriers here, and they were blocking some of these stations. And, the question was, do we have too many carriers? Because these carriers were used to build the assembly. So what we had was an experiment manager here, and this tool would allow us to change. So we're going to optimize for throughput per day. And we did a design of experiments. We went from 10 to 100 carriers, increments of 10, and we changed the line speed from 1 to 5 meters per second in increments of 1 meter per second. And we did this test, and it did all combinations of those to see what was the best set of results. So here I can actually see my results, and it's going to come back and show me after this was done that here's a table of, I had 10 carriers at 1, 2, 3, 4, 5 meters per second, 20 carriers at 1, 2, 3, 4, 5, and I had this big block of examples. So if I look at the visualization, when I was at 10 carriers, I definitely wasn't doing it enough volume. 20 carriers, but when I hit 30 and so, I was getting the volume. But, it's kind of unique. The more carriers where they went, they got less volume. So here at 30 carriers at 2 meters per second, it was the optimal setting. This was unique because they were running 65 carriers in roughly 4 meters per second. So they were double the amount of carriers and double the amount of speed. And while this was not a big, we weren't asked to do this, but we noticed it. We ran the experiment. We hit the button, the computer ran for a day, and it came back and gave us the results. So we told the customer, hey, take off some carriers and slow it down, and you'll get more output. And they kind of laughed at us, make it slower. Yeah, right, that's going to make it faster. And I don't know, 4 or 6 weeks later, we get a phone call on a Monday. Hey, we tried it over the weekend. You're right, it works. So what happened was the whole line increased output by 16%. So in essence, we took out some carriers and slowed it down, but it optimized things. I don't know if you saw this being backed up all the way over to here. These stations couldn't put throughput in because there was too many carriers. And when we slowed it down, the speed going through things, the parts were arriving at the exact right time when the station was empty so they could get in there. Because when it was going too fast, they were getting lined up and backed up, and they were blocking cells. So if I tried to put this area was backed up, it would stop this one from working. So I'd have to clear this one out before I could work here. So it actually was slower because it was backing things up because it was going too fast. So this was unique, 16% additional output, and we didn't change anything. We didn't add any people, any equipment. 318 additional units were built every day, and they figured it increased profits by 15 million annually. The company was extremely upset that we found this because they've been running this plant for 3 years before we found this, and they could have made another $45 million. So after that, this company now uses this tool on a regular basis to optimize things. But here they had a production target. We exceeded it with the same tools by tweaking it. And, very powerful tool to allow me to do that.
So Curtis, you could say that that company, that essentially they were failing, and then they got this software, and then it was what that video said. What would you do if you couldn't fail? So for them, they were getting $15 million extra per year without doing anything extra.
Right.
So that's the digital twin of not failing then.
Right. They were not, the problem was they didn't know they were failing. They thought they were doing good. They had a quota that they wanted to make, and I forget what it is, it was like 2,400 units a day. And they based all their profit on that. And when they got there, they were happy. we just found out that they could do more. So, here they weren't really failing, but use the simulation tool, we not only failed, we surpassed their expectations. So if you knew you couldn't fail, let's look at it the other way. Let's say their profit margins had to be at like 2,700 units and they were making 2,400 units a day. Well, they're failing, and how do you make sure you don't fail? Well, I can use these tools to optimize, and maybe I could make it cheaper by removing labor or changing other things, but I can, the goal is I know what the simulation is going to do, and I can prove it and optimize it, and I know I'm not going to fail because I've proved it's going to work through computer simulation.
Yeah, cool.
So the next tool I want to talk about is Process Simulate, and it really focuses on robotic applications and not failing with that. So back, in days of old, when bodies were put together, they were, just manually put together, but now we simulate the entire body. So body build between the side and the roof panels. The other side of the body is missing, but we could go in and actually simulate the robotic path and make sure it goes around clamps and everything. So here's a view of Process Simulate. You can see this robot here at 6 o'clock. It is putting a part into a fixture and it's staying there. There's a sensor there that says there's a part presence, sensor that says there's a part there, but it cannot move until this robot comes in and picks that part up, and the part is now gone, and now it can move and go off. So we actually put sensors in there. It's a discrete event simulation. Things have to happen before stuff is allowed to go, and you can actually see these little toggles changing from red to green, because those are the little different switches that are turning on and off. But we can simulate the whole plant on all these cells, and what is great is the way we program this is what we call inverse kinematics. We tell the robot, like this one here, where it has to go. Let's pick on this one. It has to come over here, so we give it that point, we give it this point, and then the robot figures out, the software figures out how to make the robot get there. So all the programming that you did manually through, manual input through keypads and everything, this is doing it for you. And what's nice is when I get done, I can export it. There's libraries of all the major brands of robots, and we know how they react and how they move and how they reach. Nice thing is I can also do reach studies. I can make sure I can reach everything. If I couldn't reach this portion here with my end-arm effector and that spot, I might have to move this base, and it gives me tools to help me move that and figure out how to get there. So it's a very powerful tool for programming robots. Many of the, I'm going to know the auto industry well, many of the automotive manufacturing companies require this simulation for their body shops just because they know the parts are going to be able to reach, the robot's going to catch everything, and there's going to be no crashes because I can check for interferences and crashing. Oops. In addition to it, why are you advancing on me? Because it's not being nice. All right, I'm not sure what happened there. Just give me a quick second here. And I'm going to go on my slideshow. There we go. For some reason it wasn't working. So here I have this weld station here, and this is being done in Process Simulate. One of the great things is I have this simulation, and I was saying I had sensors and all that good stuff. We can actually do what they call virtual commissioning. You have to commission your tools on your floor. Traditionally, you wait until all the tools showed up, you got them all working, you got them all wired up, and then you start testing the code, your PLC code, your HMI codes. Well, what's great about this tool is the simulation can actually simulate your tools that are on the plant floor, and I can run my PLC code, and this happens to be my HMI code here, and I can test it. So you can see here, this is going through. If I had closed, the clamps close, they open up. If I put my dumps in, dumps out, I'm actually testing the interface on my HMI with the operator be pressing in his buttons to make sure that things are operating the way they should be. If they're not, I can adjust and fix my code. Nice thing is, I'm doing it from my desk. I'm using simulation. I'm not in some plant doing this. And I'm doing this before I get to the plant floor. This is great for many things. I know when I get to the plant floor, I'm going to be there a lot less time because I've proven out that my code is doing the functioning it's supposed to be doing. In this case here, I've just added my second part. I can actually see my robot come in. It clamps it. It can do the welding. It moves around the clamps. It doesn't collide with anything. And I can validate that everything is working properly. And not only is the simulation working, but my PLC code and my HMI code is all being tested. So here we have an example. Cuco in Brazil had a robot line where they were doing door hemming. So they were building up doors for a car. And for those of you who are not familiar with door hemming, but if you ever open up your car doors, the outside piece of sheet metal kind of goes to the edge and then wraps around and folds over the inside piece. That way it's a smooth, round corner edge. That's what they mean by hemming, right? So here we had a couple of robots that did adhesive applications. There was one that was material handling, just move the parts around. The roller hemming, which is the hemming process, and then they have a respot, which is after it was put together, they keep welding it a little bit more. There was one PLC and two HMIs. They wanted to do virtual commissioning with this system. So they did a simulation of the product, and you can see all these little lines, reds and greens. These are all the switches and controls and sensors, and we can actually see what's going on here. So when these sensors are being tripped, we can actually see them being toggled there, right? So those sensors are going to be tied back into, they also put the safety interlocks. If you open up a safety gate, it would validate that it closed the line down. But with the virtual commissioning, I would take the virtual commissioning, look at these sensors here, and that would be my input into my PLC. So when the sensor got triggered, the PLC would understand that. And then the PLC would give instructions to the simulation to operate. So machines would move, clamps would clamp, motors would turn, and then more sensors would happen, feed it to the PLC, and then it would give the next set of commands to the tools. So, but we tested all that stuff up front. They figured it took 30% less time to engineer it. And this was their first project. But the big thing was after all the tools hit the shop floor, it was 6 hours from the time everything was set up and running to they could actually get to full production. Normally this was a 2-week process for commissioning. They got it down to 6 hours. And since then they've been sold and they use this universally in all their products.
Hey Curtis,
Yes,
on that process simulate, it just reminds me of an example that we saw in our area where one of the big OEMs, they were going to have a changeover on the shop floor. And so they typically do those changeovers, around the holiday when there's a shutdown. And because they didn't use the digital twin, they brought in all this equipment. They started to put it in and nothing worked. And so then it was a mad scramble to try to put back the old equipment. So that really is the case of an epic fail, if you will, because then they got to wait for the next time. So tools like this are really going to help where you can make sure everything's right the first time, ahead of time.
Yes, getting back to that, if you knew you couldn't fail, in this situation, they didn't know they were going to fail, and they failed miserably. It was for a very high volume product, and they were doing a mid-year model change. And when they did it, it failed. They had to reverse back. And the problem was they had to wait until, they normally would have waited until the middle of July, but due to COVID this year, they actually got it done early because the plants were shut down a bit. But they, had to delay that product launch 6 months. And the company that did the programming for all the controls and everything had to, tuck their tails between the legs, go back home, fix everything. And at that point, the OEM said, thou shall use virtual commissioning. And that's how we know about it, because we got involved at that point to help these folks to make sure that everything ran in the virtual world, found their problems, found their bugs, got them fixed. Then they went to production. And in this case, it was just slow. But I mean, sometimes, you have crashes, you have, things that crash and break. And when that happens, it costs weeks and or thousands of dollars to fix it. And you don't want to do that on the plant floor. If you use the digital twin, I can make sure I don't fail by doing virtual commissioning and, using the digital twin to prove everything out. So good point. Thank you, Dan. So the third tool, first one was plant level. The second one was kind of focusing on robotic cells, but this one is kind of focused at the machine level. So Mechatronics Concept Designer. So here on the left, I have a little index machine doing some assembly, and I have a bunch of sensors, limit switches, all types of things on here that are sending signals to my PLC. On the right, you can actually see the status of those signals here. So as things happen over here, it sends it to the PLC. Then the PLC sends directions to make this linear slide move, to index in and out, to clamp and unclamp parts as it's picking it up and moving it. Eventually, when all these stations are done, this indexes. It's sending all those signals based on, as I'm saying, it's sending all those directions based on the signal input over to here. So signals are going to the PLCs. The PLC is then sending commands back to the tools, just like the real tools. So we're emulating or virtually commissioning the software code in your PLCs and your HMIs. The great thing is I can do my safety testing. What if I hit the e-stop button? What happens? I can do that testing. What if I hit the e-stop button, somebody went in there to fix it, and they left the slide in the wrong position? How does it restart? You can test all those things. I can do all my safety testing in this virtual world in a nice clean environment and fix it at my desk versus doing it on the plant floor. So virtual commissioning and the digital twin is a great combination.
On that, when it comes to that PLC code, being able to test it, we actually spoke with a company just a week or two ago, and would you believe that they allot 6 weeks for debug time? So once the machine's built, they say we got to have 6 more weeks for that. So with MCD, could they get started with their programming a lot earlier then?
Oh yeah, what's great about this is once I have this digital model made, I'm gonna go have to make the tools, right? So, in CAD, oops, I'm sorry, hit my scroll button too fast. So in CAD, I had to design all this stuff. Now that I have that, and even early versions of CAD, my controls team can get in there and start doing their programming. But once I have this, I can do all this testing before my tools were made. So, before what we used to do was you designed, your mechanical guys designed their product, and then you had a controls team that did all the programming, and it was kind of thrown over the wall. Then tools would be made, they'd show up on the plant floor. Then I would do my commissioning. Well, what we're doing is taking this commissioning and moving it up earlier in the line, and instead of doing it in sequence, I'm doing it in parallel because I'm doing it virtually. Now, when I get to the plant floor, I still have to make sure my wiring is correct. If these are lights here, and they're changing color, we've got to make sure they didn't wire it wrong, so this shows up, red when it should be green. They got to do some of that testing. But the logic will be tested and it'll be proven out. So there will still be some commissioning on the plant floor, but instead of 6 weeks, it might be days or hours, depending on what it is. So good point, Dan.
Thanks.
So here we have an example. So on the right, I have my model being completed. On the left, I have an HMI. But riskless test, watch this. I mean, I crashed into my table bed, right? If I did that in real life, that would be thousands of dollars, you know, tens of thousands of dollars, depending on what it is, and might delay my launch by weeks. I tested it, found it, fixed it, you know. So it's quite versatile. Here I can even do multiple things. I have a robot that, you know, doing some assembly, light assembly in this machine. I can test working correctly. Even something simple as a tool change. I go to grab it and I can see I'm off. I can stop my simulation, physically measure the distance that's off, and then go into my PLC code and take that dimension, so it's almost 20 millimeters, come up here and modify that, and away I go. And I can rerun the simulation, and voila, it works. So I can find these bugs, fix them quickly, fix them efficiently, and there's no risk. I'm not damaging anything because my tools, I mean, I've seen folks do virtual commission testing, and they have a person who's sitting with his sole job to have his hand half an inch away from that little red e-stop button. You know, and there's probably a couple people out there chuckling, going, yeah, I know that guy. Because when they're testing it, he's ready to stop it and say something dangerous happens. And so here, I can do riskless tests, and when I get done, I know I'm not going to fail, and that's the key. So going from my tools and everything, I'm going to talk about a variation analysis. And it's for 3D tolerance analysis, and it includes the variation for the parts, for the part tolerances, and the variation introduced by the manufacturing process of putting it together. So, I don't know if you remember a few years ago, General Motors, they had a recall for ignition switch problem, right? So it plagued them a little bit, but they had a lot of statistics here. But 1.5 billion it cost them, right? 26 million cars were affected. But what was unique is they had a program where if you thought your car had a problem, you brought it into the dealer and they give you a loaner. So they had 52 million used cars to sell because they loaned them out, plus those 26 million cars to fix. So what was the problem? So the ignition switch goes through a column. At the other end, there's a little rotating piece that has a little detent spring that would lock into position. Well, it wasn't optimized for all the variation cases that were out there. And the fix was just making that little piece a little bit longer. It wasn't much. So, but it was very costly to General Motors. Right? But a couple years before that, Toyota and Lexus, they had a thing people were calling it the floor mat problem. But it wasn't really a floor mat problem. What it was the accelerator pedal, right? So this accelerator pedal, it affected 4.2 million cars. They shut down 6 assembly plants, some for 3 weeks. And if you can imagine the cost of shutting down an assembly plant for weeks, very costly, right? So what it was the assembly pedals, back in the day when you had carburetors and springs, there was a feel to the pedal. So when that pedal pivoted, they had this little piece that would kind of go under some notches to give some drag and give some feel like a spring, right? The problem was it was going in too far and actually locking the pedal in place. So it was locked in, full accelerate problem. So the fix, they just put a spacer in there. If you notice, there's a little bump out here that stop it. They just made it a little thicker. So it was basically a little piece of steel with some double stick tape on it, 10-cent fix, right? Well, it cost them a lot of money for that 10-cent fix. So what did these recalls have in common? Cost billions of dollars to fix. Damaged corporate name. Up until then, Toyota and Lexus were the golden childs. They didn't have problems like GM, Ford, or Chrysler. They didn't have recalls. Lost customer loyalty. I know a lot of folks, I work here in the Detroit area, these people would say, I'm not going to buy another GM product. I'm switching over to brand X, Y, or Z because, the switch problem is too, much of a problem for me to come back. But they were caused by designs that were sensitive to variation, because it only happened on some of them. And all of these recalls could have been avoided through the use of computer simulation, the digital twin of the variation. So this is how the tool works. This happens to be a shifter, an automatic shifter for a car. That green part attaches to the cockpit instead of the floor. But the handle pivots. When it pivots, it pulls this bracket. That bracket pulls this cable out of a sheath. And how much that pulls out tells the transmission what gear I'm in, whether I'm in park, neutral. You can see the variation here. The builds are going from build to build. That's the part tolerance and the assembly processes that add variation to this. And we come back and we actually see how good we are. So we're predicting how good we are. We're at 3.36 mils of variation. We should be at plus or minus 1 mil. 8% of the builds are falling out of spec. That 8% of the area here in red. So, but knowing that we have a problem is one thing, but knowing who caused it is another. So there's a built-in design of experiments tool, and 50% or 47% of the variation is coming from the plane that pin pokes into. That plane is perpendicular to the measurement I'm making. So a lot of folks wouldn't put that in a manual tolerance stacks, but this 3D tolerance stacks identifies it. Now that I know that, we can fix it. What's unique is if this thing came back and went into the drive position from where it is in park, this bracket becomes a little more perpendicular to this line. As it pivots up, it becomes more horizontal. The biggest amount of variation was the amount of gap, and it was a 1/10 of a millimeter gap on each one of these that became the #1 contributor. So it changed. This was the perpendicularity of that plane down here to that pin. So that plane tipped, that pin tipped with it, and it pulled it. But here it was just taking this bracket and putting on these two nuts, or bolts, I'm sorry. So redesign was done, and we solved this problem before it went into production, and it was not an issue. Had a company that did medical staplers. They want to make sure all staples went together and curled in. They didn't curl out like sometimes that happens, and that was their big concern. So we made sure that didn't happen. We had problems in the beginning. We fixed it. It was great. But the bigger benefit they had to this was they typically they ordered 200 sets of parts to make 1 or 2 working prototypes. The way they do it is they grabbed a part out of the box or the bin of parts, grabbed a second part, try to put them together. If they didn't go together, they take the second part, put it on the table, grab another one, and they kept doing it, and they kept testing and trying until they got 1 or 2 working prototypes. On this program, all 200 prototypes went together the first time. Company, realized the value to using a tool like this, not only to make sure that they didn't have any risk, and they knew they were going to succeed and not fail with the staples, because since this was a medical stapler, they didn't want any, problems with that, because that would be very, painful, not to be a pun there. But they also got these prototypes to go together, and they proved to them that this is a value-added tool to make sure this digital twin of the variation, that they could succeed and meet all their expectations for parts going together and fitting and functioning right.
Yeah, you don't want them to fail on you while they're in the surgery.
No, it's one thing to fail on, a coffee maker leaking. It's another to have it fail in the middle of a surgery. That's a bad thing. So, had another company here that was doing a new design for airplane, and this is like about a 10-inch section through a wing, and then you could see the flaps in the back, and they had a dual flap design, and they wanted to make sure that the linkages didn't bind with this new concept, and what they wanted to do was make sure there was a nice tight gap here, and the trailing edge was within spec. They wanted to hold it within plus or minus 30 thousandths of an inch. And you wanted it equal from side to side of the plane, because if one was down, the other side was up, you'd be turning. Well, the problem was when we got done doing this, we exceeded the factor by 10. So instead of plus or minus 30 thousandths, we were like 380 thousandths, plus or minus. The biggest contributor, 60%, was plus or minus 1 millimeter tolerance on this 360. It was the true position of that hole there, but that was tied to a little linkage, This pushes it out. This little linkage attaches to a bigger one, attaches to a bigger one, attaches to a bigger one. And what happened was it exponentially grew. We figured it out, we redesigned it. They figured this 2-week study saved them at least 1.2 million euros in retooling. So, but it was done early. We did the digital twin of the variation, improved that we wouldn't fail, or we would have failed with this design, and we fixed it. So, how do you mitigate your risk? We talked about these risks before. Do we use something like the crystal ball, or do we do it, I'm going to say, the traditional ways? I never did any of those traditional ways. Before, when I was younger and in this industry, I used the lucky horseshoe. Much better method than those 3 right there. So, but I mean, seriously, if I want to make sure I don't fail, I use the digital twin to make sure that I have successful assembly and manufacturing tooling and processes to make sure my product meets its production targets and quality targets. So do not gamble on meeting manufacturing targets. Your company's future depends on it. So going back to one of the original quotes I had there, if I told you I had a crystal ball that lets you mitigate manufacturing risk to make sure you do not fail with your future product launch, would you be interested? That's what the digital twin is. So with that, if you have any questions or comments or like to learn more, please contact Steve Arnold. His contact information is there. If you want to take a screenshot of that with your phone, please do so. That way, we can follow up with you and answer any of your questions. So with that, Dan, are there any questions?
Well, great job on your presentation as always, Curtis. There's no questions in the chat, but if anyone has a question and you'd like to just unmute your mic, feel free to do so, and we can field your questions as the best we can.
Hi, Dan. Mike Warren here. Yeah, had a question. This reminds me a lot I might be showing my age here when a piece of software like this reminds me a lot of The Sims, or like a life simulation type tool for manufacturing and industry, which is that's super cool. The one point that comes to mind is spinning up a tool like this. Is there kind of any guidance you have for the time commitment it takes to set up a tool like this? I mean, once it's set up, it looks invaluable, right? But there seems to be there's some sort of time commitment and energy at the beginning to, put things on the floor, get the measurements correct. I wanted to see if that's something like, days, weeks, months, order of magnitude.
Yep. Well, as a general rule, we talked about a couple of different tools here, but is 3 to 5 days worth of training, depending on how deep you go into this, if you do the virtual commissioning and the learning of the tool. We found some of these tools, if you get the right person. So I'm going to pick the last one we were talking about, the variation analysis tool. If you have somebody who understands GD&T and understands how to measure things on the plant floor and problems that come with that, it's fairly quick and easy and intuitive to them. But if you take a product designer who's going to do this but doesn't really know GD&T and never, seen the plant floor and how things, it takes a little more learning curve. So it depends on the toolkit, that comes with the person. If I'm teaching somebody a new CAD tool, if they learned one before, it's pretty easy because I just got to change you from file exit to file close. You understand the function, you just need to understand how to do it. So, the learning curve we found for people that, have experience using the tools, anywhere from 2 to 4 weeks, they're very productive. At 2 weeks, they're crawling, and, maybe at 4 weeks, they're walking. At 2 months, they're running, so, but it depends on the tool, because you have to learn the concept. And one of the things that we do as a company is we offer a program that, where we can actually work with your team to maybe do the first model together, where we do most of the work and you're looking over our shoulder. The next one, we do it jointly, and the third one, you're doing it and we look over your shoulder, so we have regular conversations to make sure your team succeeds. Or, we have other companies that just buy it, take the training, and they're off and running because they got people that are, knowledgeable about it or want to learn it and go. So it's a mixed bag of things, but, I'm going to say 2 to 4 weeks before you're proficient, depending on who the student is that's learning the new tool.
Sure, and that seems to line up with the intake of information that's available, right? Like for new machines and stuff that might have been completely designed in CAD, this is absolutely a no-brainer. Yeah.
Yep.
Those are great tools.
And if they're not done in CAD, we actually, Mechatronics concept designer, Dan is our resident expert on that. He's my partner in crime here. He's done things with just sketches, the mechanics of the tools twisting and moving. It looks like line art on a PowerPoint, and he's been able to do it with that because you did it so early. It was before they're trying to concept which way to design the tool, and this can prove out the concept, and then as the detail of the design progresses, it gets finalized and get a little more polish. But up front, it's just lines moving.
Yeah, and I can just add to that because Michael, you brought up the example of the games like The Sims. Those were fun to play. Well, using these tools, it actually becomes kind of fun. And so whoever we've showed this to, they, as it were, they got a smile on their face as they're using it. So it's not such a frustrating thing to use or such a difficult thing to use that you're frustrated, but more so intuitive, so you enjoy it.
Hey, Dan, you're showing your inner nerd by saying it's fun.
I know. I hope this is not recorded. Oh, wait, it is.
This is the right crowd, though, I think.
Any other questions? Well, great. I thank everybody for attending. And again, if you take a screenshot of this, there'll be some follow-up emails for those of you who attended. But there's Steve's contact information there, and Steve will get a hold of us, and we can figure out what to do and how we can help you, and maybe go a little more in depth on your specific problem and how it can be solved.
Thanks, Curtis and Dan.
Thank you.
Thanks, everybody.
Thanks very much.